All right, review video part 4. We are going to talk about Taylor and Maclaurin series here. I'm actually going to go into a little bit more depth on this because A, sometimes this means more review, and B, sometimes it's hard to get to this in our sequence. So as a reminder, so far we've done all these problems. We've done a bunch of sigma notation things. Do they converge or diverge? And then by what test do they converge or diverge? We got into the ratio test. We used some alternating series test. And we sort of got to finding radius of convergence and interval of convergence, like this one right here. And this seems like we're going in a different direction when we start talking about Taylor and Maclaurin series. And we'll connect them. But right now, I want to back up a little ways and do a tangent line problem. And we'll connect that to the Taylor-Maclaurin series as well because they're kind of sort of the same thing or similar things. So find the equation of the tangent line to y equals root x at x equals 9, and you use it to approximate the square root of 9.2. So you're going to plug in you're going to plug in x equals 9.2 to your tangent line after you get it. Look, so I'm going to talk in a moment, but I encourage you to hit pause. Try this. Do it. You can do it. You know how to do tangent lines. So hit pause, do this real quick, and then we'll do it together. Okay, here we go. So to find the tangent line, whenever I see tangent line, I do y minus y1 equals m times x minus x1. And then I need to find my different pieces. So x1 is definitely 9. Y1 is that value plugged into the function. Square root of 9 is 3. I'll write that equals root 9, which is 3. And then m is y prime, not y1, y prime of that 3 value. Or sorry, not that 3, that x1, which is the 9. My bad. So y prime of 9, which got to take the derivative of root x. You should know that in your head or be able to do it quickly with power rule. It is 1 over 2 root x. That's what we do anytime we're looking for m with a tangent line. Take the derivative. And I'm going to evaluate that at x equals 9. Remember, when I have just a big long bar like that, and one value at the bottom just means plug it into the function. It's different from doing a definite integral, which you should also know how to do. All right, anyway, that gives me 1 over 2 root 9, which is 1 over 2 times 3, which is 1 over 6. So m is 1/6. So what's that give us? Y minus 3 equals m, which is 1 over 6. Times x minus 9. All right, cool. So that's the tangent line. If that's all we're asking for, we'd be done with this problem. But notice we're being asked to approximate root 9.2. So we want to do an approximation for this function using the tangent line. So I'm going to just plug in 9.2 to the tangent line. So what's that give me? Y minus 3 equals 1 over 6. Times 9.2 minus 9. Notice the 9.2 and the 9 are easy to subtract. It gives us 0.2. So it gives me y equals 3. I move that over to the right-hand side by adding to both sides. Plus 1 over 6 times 0.2. And a variety of ways that we can kind of work with that. In this case, I'm just going to give you the decimal approximation, which I could plug into my calculator and get 3.0. 3 repeating. So if that's what we're being asked to do, that's what we would do. A Taylor series is really similar, except for instead of just having an m, it's got more pieces. So I'm going to write what a general Taylor series out for you. I'm going to use T for Taylor series is it's f. Actually, here, what I'm going to do. All right, kaboom. Whoa, there's some things. Say I was asking you for a tangent line But instead of giving you like 9, I just said a. And instead of giving you root x, I just said a function, right? So we would take y minus y1 is m times x minus x1. And I'm just going to let x1 equal a. So that's going to be a. And then instead of y1, I'm just going to have f of a. And instead of m, I'm just going to write it as f prime of a. So notice if I zoom in, this line right here is really just an alternative version of this with f's and with a's instead of y's and x's. And then notice what I can do is take this guy and move it over to the right, just like we did with this 3. And I can write it as y equals f of a plus f prime of a times x minus a. It's just another way to write a tangent line. So that should make some sense. Should maybe feel a little obscure or abstract without equations and numbers, but that's okay. It's just a tangent line. So now I'm going to write what a Taylor series is. A Taylor series at x equals a, and I'll explain sort of the same thing that we have up there, is t equal to f of a. Notice that's the same as what we have right there, plus f prime of a times x minus a. Again, this right here so far is exactly the same as a tangent line. What a Taylor series is instead of using just the value and the derivative, so the f and the f prime, we also use f double prime and f triple prime and so on and so forth. So here come the extra pieces that are part of a Taylor series that go beyond just doing a tangent line. So instead of f prime, I'm just going to add a bunch of terms, right? They're all going to look really similar. Instead of f prime, what's the next one going to have? F double prime of a. And then what I'm going to do is I'm going to divide it by 2 factorial. And that comes from somewhere. I'm not going to explain it right now. And then instead of x minus a, I'm going to write x minus a squared. And what this is going to do is it's going to match second derivatives for the Taylor series in some function. So plus f triple prime of a over something factorial. The double prime had a 2. What's the triple prime going to have? You're right, a 3 factorial. Times, we are going to get an x minus a, but instead of squared like we had for the double prime, we got a triple prime. What are we going to get? We're going to get a cubed. Plus dot, dot, dot. We can go out as far as we want and include as many terms as we want. We can go out to infinity, and that's where the whole summation things come from, but I don't want to use too much time to talk about that right now. So a Taylor series is just this form. It's like a tangent line, but an extension of it that is going to work better than a tangent line. So you may say, okay, that's a Taylor series. What is a Maclaurin series? Well, a Maclaurin series is just a Taylor series where instead of at x equals a, we are always using x equals 0. So anywhere there's an a there, I'm just going to change it to a 0. So I'm going to use m for Maclaurin is f of, what do we take? 0 plus f prime of 0 times, now this is where it's going to simplify. All right, I have x minus a here. Well, if a is 0, x minus 0 is just, yep, you got it, 0. So we're just going to have x minus 0, which I'm just going to write as x, plus f double prime of 0 over 2 factorial times, well, when I take the a and make it 0, what are we going to get? X squared plus f triple prime of 0 over 3 factorial times, you got it, x cubed. What's the fourth term going to be? Well, it's going to have f fourth derivative over 4 factorial times x to the 4th, and so on and so forth. And they just go on for forever. So let's do an example that's similar to what you might be tested on. So here's our question. It says, let f be the function that has derivatives of all orders for all real numbers, blah, blah, blah. All right, then f of 0 is 6, f prime of 0 is negative 3, f double prime is negative 4. Notice these are all these values here. And then f triple prime is 48. So that's this here. They say write the third degree Taylor polynomial for f about x equals 0. About x equals 0 just means that the a value that we're doing it at, we're building this series, is 0. So you should see that since this thing is built about x equals 0, it's just a Maclaurin series. It's just this right here. So I got to go and use this formula, and this is something that you should know heading into any tests on, like the AP test on this that has this series stuff on it. And then it says, use the polynomial found in part A to approximate f of 0.3. Notice 0.3 is really close to 0. So it's just like this tangent line question. Find an approximation and then plug in the value that we have. So let's go ahead and do that. And I want to leave that there. So since they used Taylor right here, I'm going to write, I'll write M for Maclaurin because I do know it's a Maclaurin series. So my approximation is f of 0. That is 6. Where do we get that? From right here. And I'm just kind of using these right here. Okay, plus f prime of 0, which is negative 3 times x. And that's just that term, so that value times x. And I'll fix up the plus and the minus there in a moment. And then plus, I get a fraction bar. I get a negative 4 over a 2 factorial times x squared. That was the double derivative with a 2 factorial and a squared. Well, what's the triple derivative going to give us? It's going to give us 48 over 3 factorial times x cubed. And then I do want to go ahead and simplify this. This gives me 6 minus 3x plus, all right, 4 divided by 2 factorial is 2. So 4 divided by, that gives me a minus 2 because I do 4 divided by 2 factorial, x squared. And then 48 over 3 factorial is 48 over 6 because 3 factorial is 3 times 2 times 1, which is 6, which gives me 8 because 48 divided by 6 is 8. So this next one gives me plus 8 times, I don't even need parentheses, 8x cubed. So, like, that's it. That's the answer for part A. As long as I know this little formula that we wrote down up there, we can work out what that series is. And then it says use the polynomial in part A to find f, or to approximate f of 0.3. So what I'm going to do is write m of 0.3, and I'm just going to plug in x equals 0.3. So I'm going to get 6 minus 3 times 0.3 plus, minus, keep making that mistake, minus 2 times 0.3 squared plus 8 times 0.3 cubed. And now hopefully I have a calculator to do some of this, because if I type this all in, I can just punch it into my calculator, and I wind up getting 5.136 if I go accurate to 3 decimals. And that's it. I can do this polynomial, or I can do this Taylor series / Maclaurin series question. I'm going to stop here. I'll pick up in the next one where we're going to go ahead and do one that's not built about x equals 0, but that is built about another x value. Hopefully this is making sense.